Chapter 4 addresses the forward kinematics of open-chain robots, as illustrated in this video of a robot with 6 revolute joints. We define a frame S fixed in space, often at the base of the robot, and a frame B at the end effector of the robot arm. If we command the robot to move, the B frame moves. The forward kinematics problem is to find the configuration of the B frame relative to the S frame, given the vector of joint angles theta. The transformation matrix representing the B frame and the S frame is TSB of theta, or just T of theta for short. To derive a procedure to calculate T of theta, let's use a simple robot arm that moves in a plane. This robot has 3 joints: a revolute joint, a prismatic joint, and another revolute joint. You can also see the stationary S frame and the end effector B frame. This is a stick figure version of the robot. The joint variable theta1 represents the angle of joint 1 relative to the horizontal. Theta2 represents the extension of the prismatic joint, and theta3 represents the angle of joint 3. The 3-vector theta is a list of 3 joint variables, and T of theta represents the configuration of the B frame relative to the S frame. If we set all of the joint variables equal to 0, the robot is in its home position as shown here. We write the 0 configuration of the B frame as T of 0, or simply M for short. At the 0 configuration, the B frame has the same orientation as the S frame, and the 3 in the top right element of the M matrix means that the B frame is 3 units from the S frame in the XS direction. Now say we rotate joint 3 by pi over 4 radians. The theta vector is now 0, 0, pi over 4. This motion of the B frame can be represented by a rotation about the screw axis of joint 3. Since it is a revolute joint with no translational motion, the screw axis has 0 pitch. Because positive rotation is in the direction indicated in the figure, by the right-hand rule, the screw axis is out of the screen, toward you. As we learned in Chapter 3 videos, the screw axis can be represented in any frame. Let's represent it in the S frame, and let's call joint 3's screw axis S3, consisting of an angular component omega 3 and a linear component V3. Since the screw axis involves rotation, omega 3 must be a unit vector. Positive rotation is about an axis out of the screen, which is aligned with the S frame's z-axis. Therefore, the unit angular component is 0, 0, 1, a unit vector aligned with the zs axis. To visualize the linear component V3, imagine the entire space rotating about joint 3, visualized here as a turntable. Then V3 is the linear velocity of a point at the origin of the S frame when the turntable rotates with unit angular velocity, as shown here. So V3 is 0, minus 2, 0, meaning that the origin has a velocity of 2 units in the minus ys direction. V3 could also be calculated as minus omega 3 cross Q3, where Q3 is any point on the joint axis represented in the S frame. Now that we have the screw axis S3, we can calculate the B frame configuration T of theta. We simply apply the space frame transformation corresponding to motion along the S3 screw axis by an angle pi over 4. This transformation is e to the bracket S3 times pi over 4 using the matrix exponential from the Chapter 3 videos. Since it is a space frame transformation, it pre-multiplies m. Now suppose we change joint 2, extending it by 0.5 units of distance. The theta vector is now 0, 0.5, pi over 4. The screw axis S2 corresponding to joint 2 has 0 angular component, omega 2, so the linear component V2 must be a unit vector. If we imagine the whole space translating at unit velocity along joint 2, a point at the origin of the S frame would move with a linear velocity V2 equal to 1, 0, 0, expressed in the S frame. Therefore, the screw axis S2 is defined as 0, 0, 0, 1, 0, 0. The new configuration of the B frame, T of theta, is obtained by left multiplying the previous configuration by e to the bracket S2 times theta 2. It's important to notice that the previous motion of joint 3 does not affect the relationship of joint 2's screw axis to the S frame. That's because joint 3 is not between joint 2 and the S frame. Therefore, S2 is the same as the screw axis of joint 2 when the robot is at its 0 configuration. Finally, let's rotate joint 1 by pi over 6. The theta vector is now pi over 6, 0.5, pi over 4. The screw axis S1 is a pure rotation about an axis out of the screen, so the omega 1 vector is 0, 0, 1. Rotation about this axis does not cause any linear motion at the origin of the S frame, so the V1 vector is 0, 0, 0. The new configuration of the B frame, t of theta, is again given by left multiplying the previous configuration by the new space frame transformation. Again, the previous motions of joints 2 and 3 do not affect the relationship of joint 1's screw axis to the S frame because they're not in between joint 1 and the S frame. Therefore, S1 is the same as the screw axis of joint 1 when the robot is at its 0 configuration. For any serial robot, the procedure generalizes directly. First, define the M matrix representing the B frame when the joint variables are 0. Second, define the S frame screw axes S1 to Sn for each of the n joint axes when the joint variables are 0. Finally, for the given joint values, evaluate the product of exponentials formula in the space frame. In the next video, we'll see an alternative version of this formula in terms of screw axes expressed in the B frame. In the previous video, we derived the product of exponentials formula to calculate t of theta, the configuration of the end-effector frame B relative to the fixed space frame S when we're given the joint positions theta. In that formula, the joint screw axes are defined in the S frame fixed to the world. In this video, we derive an alternative version of the formula where the joint screw axes are defined in the B frame fixed to the end effector. We use the same RPR robot as an example. First, let's move the robot to its 0 configuration. As before, we define M to be the configuration of the B frame when the robot is at its 0 configuration. Now we rotate joint 1 by an angle theta 1. The motion of the B frame is a rotation about the screw axis of joint 1. We will represent the screw axis in the B frame as B1 with the angular component omega 1 and the linear component V1. Since the screw axis has rotation, omega 1 is a unit vector. Since the screw axis is aligned with the z-axis of the B frame, omega 1 is equal to 0, 0, 1. The linear motion V1 can be obtained by visualizing a turntable at joint 1 rotating and measuring the linear velocity at a point at the origin of the B frame. Since the distance between the joint 1 and the B frame is 3, the linear velocity V1 is 0, 3, 0 in the B frame. We could also calculate this by defining a point Q1 on the axis of joint 1, where Q1 is expressed in the B frame. Then V1 is minus omega 1 cross Q1. Now that we have the screw axis B1, we can calculate the B frame configuration t of theta. We simply apply the body frame transformation corresponding to motion along the B1 screw axis by an angle theta 1. This transformation is e to the bracket B1 times theta 1. Since it is a body frame transformation, it post-multiplies m. Now suppose we change joint 2, extending it by theta 2 units of distance. The screw axis B2 corresponding to joint 2 has 0 angular component omega 2, so the linear component V2 must be a unit vector. If we imagine the whole space translating at unit velocity along joint 2, a point at the origin of the B frame would move with a linear velocity V2 equal to 1, 0, 0 expressed in the B frame. Therefore, the screw axis B2 is defined as 0, 0, 0, 1, 0, 0. The new configuration of the B frame, t of theta, is obtained by right multiplying the previous configuration by e to the bracket B2 times theta 2. Notice that the previous motion of joint 1 does not affect the relationship of joint 2's screw axis to the B frame because joint 1 is not between joint 2 and the B frame. Therefore, B2 is the same as the screw axis of joint 2 when the robot is at its 0 configuration. Finally, let's rotate joint 3 by theta 3. The screw axis B3 is a pure rotation about an axis out of the screen, so the omega 3 vector is 0, 0, 1. Rotation about this axis induces a linear motion V3 equal to 0, 1, 0 in the B frame. The new configuration of the B frame, t of theta, is given by right multiplying the previous configuration by the new body frame transformation. Again, the previous motions of joints 1 and 2 do not affect the relationship of joint 3's screw axis to the B-frame because they're not between joint 3 and the B-frame. Therefore, B3 is the same as the screw axis of joint 3 when the robot is at its 0 configuration. In summary, we've derived a procedure for forward kinematics when the screw axes are expressed in the B-frame. First, define the M matrix representing the B-frame when the joint variables are 0. Second, define the B-frame screw axes B1 to Bn for each of the n joint axes when the joint variables are 0. Finally, for the given joint values, evaluate the product of exponentials formula in the B-frame. Comparing the two product of exponentials formulas in the S-frame and the B-frame, the major differences are the frame of representation of the screws and whether M is on the right side or the left side of the sequence of matrix multiplications. The 4-joint RRRP robot, like you see here, is a popular choice for certain kinds of assembly tasks. In this picture, we see it at its 0 configuration. To solve the forward kinematics, we need to find M, the configuration of the B-frame, and the joint screw axes when the arm is at its 0 configuration. Then we can use the product of exponentials formulas from the previous videos. First, let's focus on the orientation of M. From the picture, we can see that the B-frame x-axis is aligned with the minus y-axis of the S-frame. The B-frame y-axis is aligned with the minus x-axis of the S-frame. And the B-frame z-axis is aligned with the minus z-axis of the S-frame. Also, we can see that the B-frame is offset from the S-frame by 19 units in the x direction and minus 3 units in the z direction of the S-frame. We add the row of zeros and a 1 to complete the M matrix. Next, let's find the screw axis of joint 1 expressed in the S-frame. The axis of rotation is aligned with the S-frame z-axis, so the angular component of S1 is 0, 0, 1. A rotation about this axis causes no linear motion of a point at the origin of the S-frame, so the linear component of the screw S1 is 0. We can also express the screw axis as B1 in the B-frame. The joint axis is in the negative ZB direction, so the angular component is 0, 0, minus 1. A unit angular velocity about the joint 1 axis induces a linear velocity at a point at the origin of the B-frame, and it is apparent from the figure that this linear velocity is 19 units in the minus xb direction. This should be readily apparent from the figure. You shouldn't have to do any math. Now let's go faster through the rest of the joints. Joint 2's axis is aligned with the S-frame z-axis, so the angular component of the S-frame screw S2 is 0, 0, 1. Unit angular velocity about this axis induces a linear velocity at the S-frame origin of 10 units in the minus ys direction. The screw axis B2 in the B-frame is 0, 0, minus 1, minus 9, 0, 0. Joint 3's rotational screw axis induces a large linear velocity at the origin of the S-frame, but 0 linear velocity at the origin of the B-frame. Finally, the prismatic axis of joint 4 is aligned with the z-axis of the S-frame and the minus z-axis of the B-frame. The angular component of both screw axes is 0, since it is a prismatic joint. For most open-chain robots, deriving the screw axes is just this easy. You can simply look at a good drawing of the robot at its 0 configuration and get the screw axes by inspection. If anything is unclear about what we did, you should either pause this video at appropriate places or look at the examples in the book. So this concludes Chapter 4. You now know how to use the material of Chapter 3 to solve the forward kinematics of robots. In Chapter 5, we will study the velocity kinematics, relating joint velocities to the twist of the end effector. In the last chapter, we studied the forward kinematics, relating the joint positions to the end effector configuration, t of theta. In this chapter, we studied the relationship between joint velocities and the end effector velocity. Usually we represent the configuration of the end effector as a transformation matrix and the velocity as a twist. To get to the main ideas quickly though, let's represent the configuration of the end effector using a minimum set of coordinates and the velocity as the time derivative of those coordinates. Then the forward kinematics can be written x equals f of theta, where x is a vector of m coordinates representing the end effector configuration, and theta is an n vector of joint coordinates. To find the relationship between the joint velocities and the end effector velocity, we take the time derivative of the forward kinematics. Applying the chain rule for differentiation and dropping the dependence on time, we get x dot equals df d theta times theta dot. Because x has m coordinates and the joint vector theta has n coordinates, the matrix of partial derivatives df d theta is m by n. This matrix is called the Jacobian, J of the robot arm. The Jacobian is important not only for relating joint velocities to end effector velocities, but also for relating end effector wrenches to joint forces and torques, as we will see soon. Let's look at a 2R arm as an example, where x1 and x2 are the end effector coordinates. The forward kinematics are given by these equations. We take the time derivative of the forward kinematics, and we name the endpoint velocity v tip. Notice that the vector equation can be written as a vector times the velocity of the first joint, theta 1 dot, plus another vector times the velocity of the second joint, theta 2 dot. Let's call the first vector j1. Clearly, it's a function of the joint variables theta. j1 is just the end effector velocity when joint 1 rotates at unit speed while joint 2 is kept constant. We can visualize it as a vector orthogonal to the line connecting joint 1 to the end effector. Similarly, j2 is the velocity of the end effector when joint 2 rotates at unit speed while joint 1 is kept constant. Plotting them both, we see that j1 and j2 form a basis for the space of linear velocities of the end effector. We can put the j1 and j2 vectors side by side to form the Jacobian matrix J. The end effector velocity is just a linear combination of j1 and j2 with coefficients equal to the joint velocities. If the second joint angle is 0 degrees, as shown here, or 180 degrees, j1 and j2 are aligned, and it's impossible to generate any end effector velocity except along this line. I can use my arm as an example. When it's fully extended, rotation about my shoulder and about my elbow both cause the hand to move vertically. The arm loses the ability to move in some directions when the dimension of the column space of the Jacobian drops from its maximum value, and such a configuration is called a singularity. We can use the Jacobian to find limits on the end effector velocity due to limits on the joint velocity. In this figure, the set of allowable joint velocities is depicted as a square in the joint velocity space with the corners A, B, C, and D. The point A, for example, corresponds to simultaneous maximum positive velocity at both joints 1 and 2. We can map this square set of joint velocities through the Jacobian to get a parallelogram of possible velocities at the tip, including the tip velocity A corresponding to the joint velocity A. The Jacobian, and therefore this parallelogram, depends on the joint angles theta. Instead of a square of possible joint velocities, it is common to consider a circle, or more generally a sphere of possible joint velocities. This maps through the Jacobian to produce an ellipse, or more generally an ellipsoid of possible tip velocities. This ellipsoid shows that the robot can move fast up and to the left, but only slowly up and to the right. If the robot is at a different configuration, however, the ellipsoid can look very different. We call these ellipsoids manipulability ellipsoids. If the 2R robot is at a singularity, the ellipse collapses to a line segment. The Jacobian also relates forces at the end effector to forces and torques at the joints. To find this relationship, let tau be the vector of joint torques and forces generated by motors at revolute and prismatic joints, respectively. From physics, we know that velocity times force is power, and the equivalent for a robot arm is theta dot transpose times tau is equal to the power produced or consumed by the robot's motors. The robot's velocity and joint torques could instead be expressed in terms of a velocity and force at the tip, so the power can be written equivalently as v tip transpose times f tip, where f tip is the force applied by the end effector. If no power is used to move the robot, then theta dot transpose times tau is equal to v tip transpose times f tip. Using our previously derived identity v tip equals j theta dot, we get this equation. We can rewrite this as this equation using the fact that the transpose of j theta dot is equal to theta dot transpose times j transpose. Since this equation holds for all theta dot, the equation reduces to tau equals j transpose times f tip, the relationship we were looking for. For our force analyses, we assume that the robot is at equilibrium and that all joint torques and forces create forces at the end effector. No joint effort is needed to cancel gravity, for example. This equation is useful for force control. If we want the robot to generate the force F tip at its end effector, the motors must generate joint torques and forces equal to J transpose times F tip. In the case that J transpose is invertible, we also have the relationship F tip equals J transpose inverse times tau. Assuming J transpose is invertible, we can map joint torque limits to tip force limits using the inverse of the Jacobian transpose, similar to how we map joint velocity limits to tip velocity limits. In this configuration, the arm can apply large forces up and to the right at point D, but much smaller forces up and to the left. The reason is clear. A line of force up and to the right passes close to the joints, therefore requiring little torque about the joints, while a line of force up and to the left passes far from the joints, requiring larger torque. In the extreme case, if my arm is extended straight out at a singularity, I could theoretically resist infinite forces applied along the arm because the forces pass through the joints, creating zero torque. On the other hand, it is hard to hold up this book in gravity because the force requires large joint torques. This example also demonstrates that the tip force limits are in a sense reciprocal to the tip velocity limits. It is easy to apply force in a direction that is hard to move and hard to apply force in a direction that it is easy to move. It is common to consider joint torque limits that are circular or more generally spherical. In this case, the torque limits map to an end effector force ellipse or ellipsoid. As with the manipulability ellipsoid, the force ellipsoid depends on the configuration of the robot. So this video summarizes the important concepts of Chapter 5. In the rest of this chapter, we translate these concepts to twists and wrenches. In particular, in this video, we represented velocities as v-tip, the time derivative of coordinates. In the remainder of the chapter, we represent end effector velocities as twists, either in the S-frame or the B-frame. In this video, we represented end effector forces as F-tip, forces dual to v-tip. In the remainder of the chapter, end effector forces will be represented as wrenches, either in the S-frame or the B-frame. In the next video, we derive the Jacobian when the end effector velocity is expressed as a twist in the space frame S. In the previous video, the robot's end effector velocity, v-tip, was the time derivative of a minimum set of coordinates describing the end effector's configuration. The Jacobian j maps the joint velocities to v-tip. For this 2R robot, the Jacobian has two columns, one for each joint, which we call j1 and j2. Each column is the contribution to v-tip when the speed at that joint is 1 and the speed at all other joints is 0. In this video, the end effector velocity will be represented by the twist, Vs, represented in the space frame, S. We call the corresponding Jacobian the space Jacobian, Js. It also has two columns, one for each joint. Since Vs is a 6 vector and there are two joints, the space Jacobian is a 6x2 matrix. For a general open chain robot with n joints, the space Jacobian is 6 by n. Each column of the space Jacobian is the spatial twist when that joint's velocity is 1 and the velocity at all other joints is 0. To derive the form of the space Jacobian, let's use a specific example, a 5R arm whose joint angles are given by theta 1 through theta 5. Then the space Jacobian is 6 by 5. Let's focus on JS3, the third column of the space Jacobian, which corresponds to the spatial twist when the velocity at joint 3 is 1 and the velocity at all other joints is 0. If all joint angles are 0, then JS3 is simply S3, the screw axis of joint 3 when the arm is at its 0 configuration. We use this in Chapter 4 for the product of exponentials formula in the S-frame. To find the column of the space Jacobian, though, we need the spatial twist corresponding to a unit velocity at joint 3 when the robot is at an arbitrary configuration, not just the 0 configuration. So let's start moving the joints of the robot and see how that affects JS3. First, we rotate joint 5. Because joint 5 is not between joint 3 and the S-frame, the relationship between joint 3 and the S-frame is not affected by joint 5's angle. Therefore, JS3 is unaffected by joint 5's value, and JS3 is still equal to S3 at this configuration of the robot. Now we rotate joint 4. Again, JS3 is unaffected by joint 4's value. Now we rotate joint 3. Again, the configuration of joint 3 relative to the S-frame is unaffected by this motion, so JS3 is unaffected by joint 3's value. Now we rotate joint 2 by theta 2. Now we see that the configuration of joint 3 has moved relative to the S-frame, so JS3 must change. But we've drawn a new frame, S prime, that has the same relationship to joint 3 that the frame S had to joint 3 before joint 2 moved. Therefore, the twist due to a unit velocity at joint 3 in the S prime frame is just S3, the spatial screw axis when the robot was at its 0 configuration. The configuration of S prime in the S frame can be written e to the bracket S2 theta 2, the displacement achieved by the S frame by following the screw axis of joint 2 by an angle theta 2. Now we rotate joint 1 by theta 1. Again, joint 3 moves relative to the S frame, so JS3 changes. We draw a new frame, S double prime, where the relationship between joint 3 and S double prime is the same as the relationship between joint 3 and S when the robot is at its 0 configuration. The frame S double prime is obtained from the frame S prime by rotating it about the joint 1 axis by an angle theta 1. Because the joint 1 axis is represented by the spatial screw axis S1, performing the transformation in the space frame corresponds to multiplying TSS prime by e to the bracket S1 theta 1 on the left, yielding this expression for the S double prime frame in the S frame. The reason we constructed this S double prime frame is that the screw axis of the third joint is the same in the S double prime frame as the screw axis S3 of the third joint in the S frame when the arm is at its 0 configuration. So to find JS3, we just need to express S3, now corresponding to the screw axis in the S double prime frame, to the screw axis expressed in the S frame. We use our standard rule for changing the reference frame of a twist, which gives us this final expression. The same reasoning applies for any joint, not just joint 3 of this 5R robot. Joint positions of joints between the joint and the S-frame must be taken into account, while joint positions that do not affect the relationship between the joint and the S-frame can be ignored. We can generalize to this definition of the space Jacobian JS. The first column of the space Jacobian is just the screw axis S1 when the robot is at its 0 configuration. It does not depend on the joint positions because no joint is between joint 1 and the S-frame. Any other column I of the space Jacobian is given by the screw axis SI pre-multiplied by the transformation that expresses the screw axis in the S-frame for arbitrary joint positions. You can see that JS2 depends only on the position of joint 1, JS3 depends only on the positions of joints 1 and 2, etc. Notice that no differentiation is necessary to calculate the Jacobian. Also, the space Jacobian is independent of the choice of the end-effector B frame. In the next video, we will do a similar derivation for the body Jacobian, where the end-effector twist is expressed in the end-effector frame B. In the previous video, we learned how to take the joint screw axes S1 to Sn, defined in the space frame S when the robot is at the 0 configuration, and transform them to the n columns of the space Jacobian at any arbitrary joint configuration theta. In this video, we construct the 6 by n body Jacobian JB from the screw axes B1 to Bn expressed in the end-effector frame B. The body Jacobian transforms joint velocities to the body twist. To derive the body Jacobian JB, let's use the 5R arm from the previous video as an example. To derive JB, we need to define the end-effector frame B, but we don't need an S-frame. JB has 5 columns, 1 for each joint, and in this video we will focus on JB3, the third column, corresponding to the end-effector twist when joint 3 moves with unit velocity. First, we set all joint angles equal to 0. At this configuration, JB3 is just B3, the screw axis of joint 3 expressed in the B frame when the arm is at its 0 configuration. Now we rotate joint 1. Notice that this rotation of joint 1 does not change the relationship between joint 3 and the B frame, so JB3 is still equal to B3. Now we rotate joint 2. Again, the relationship between joint 3 and the B frame is unaffected by joint 2's motion, so JB3 is still equal to B3. Now we rotate joint 3. As with joints 1 and 2, JB3 is unaffected by joint 3's motion. Now we rotate joint 4 by theta 4. This motion changes the configuration of joint 3 relative to the B frame, so JB3 changes. We define the frame B double prime to be the B frame before joint 4 is rotated, and the frame B prime to be the B frame after joint 4 is rotated. The relationship between the two is given by TB double prime B prime equals e to the bracket B4 times theta 4. We define the B double prime frame because the screw axis for joint 3 is just B3 in this frame. Finally, we rotate joint 5 by theta 5, giving us the final end effector frame B, obtained by rotating the frame B prime about the joint 5 screw axis by theta 5. To find the B frame relative to the B double prime frame, we post-multiply TB double prime B prime by the body frame transformation corresponding to rotation about the body screw axis B5, giving us the equation shown here. What we really want, though, is the configuration of the B double prime frame relative to the B frame, so we reverse the subscripts, which is the same as taking the inverse of the transformation matrix. Making use of the fact that the inverse of A times B, where A and B are invertible matrices, is just B inverse times A inverse, we can write TB B double prime in this form. Since the screw axis of joint 3 is just B3 in the B double prime frame, to find JB3, we just need to use our rule for changing the frame of reference of a twist. The final expression for the JB3 column depends on the screw axis for joint 3, as well as the joint angles and screw axes for joints 4 and 5. The same reasoning applies for any joint, so we can generalize to this definition of the body Jacobian JB. The last column of the body Jacobian is just the screw axis Bn when the robot is at its 0 configuration. It does not depend on the joint positions because no joint is between joint N and the B frame. Any other column I of the body Jacobian is given by the screw axis Bi pre-multiplied by the transformation that expresses the screw axis in the B frame for arbitrary joint positions. You can see that JB1 depends on the positions of joints 2 through N, JB2 depends on the positions of joints 3 through N, etc. You can also see that the body Jacobian is independent of the choice of the space frame S. Since each column of a Jacobian is a twist, we can use our rule for representing a twist in a different frame to translate between the space Jacobian JS and the body Jacobian JB. JB is obtained from JS by the matrix adjoint of TBS, and JS is obtained from JB by the matrix adjoint of TSB. In the next video, we'll see that the Jacobian is used not only to convert joint velocities to end-effector twists, but also to understand how end-effector wrenches are related to torques and forces at the joints. Here you can see a 6R robot with a frame B at the hand. Imagine that the joints are moving according to a trajectory, theta of t. The changing joint angles theta as a function of time move the hand along the path shown in yellow. The hand is moving in free space, so it is applying no forces to the environment. In Chapter 8, when we study the inverse dynamics of a robot, we will learn how the trajectory theta of t can be turned into the torques required to move the robot along the trajectory. We call these torques tau motion of t. Now assume we choose a particular time instant t and let tau motion be the joint torques at this instant. Now assume that someone applies a wrench to the hand at this instant. Perhaps someone grabbed the hand of the robot. We will call this wrench minus FB, consisting of 3 angular moments and 3 linear forces expressed in the B frame. If we want the robot to continue to track the planned trajectory, despite this disturbance wrench, the robot's motors must create a wrench FB to balance the disturbance wrench. Therefore, the joint torque should be tau motion plus tau, where we need to know how FB relates to tau. To find this relationship, recall from physics that force times velocity is power. In the B frame, the wrench FB created by the motors multiplies the twist VB to get the mechanical power produced or consumed at the hand. This power must be coming from the motors, and we know that the power produced or consumed by the motors is the joint torques dotted with the joint velocities. If we plug in the identity JB theta dot equals VB and recognize that the equality must hold at all theta dot, we get this equation. And getting rid of the transposes, we get the relationship we were looking for. Tau equals JB transpose times FB. The exact same derivation holds for wrenches and Jacobians expressed in the space frame S, so we can generalize to the following main result of this video. To resist a wrench minus F applied to the end effector at a configuration theta, the joint torques and forces tau must be J of theta transpose times F. This result holds no matter what frame the Jacobian and wrench are expressed in. This relationship can be useful in force control of a robot. If we want the end effector to apply wrench F to the environment, we use this formula to calculate the joint forces and torques tau. In the next video, we will consider the implications of non-square and singular Jacobian matrices. We've seen 2 major uses of Jacobian matrices: converting a set of joint velocities theta dot to an end effector twist V, and converting an end effector wrench F to a set of joint forces and torques tau. The twists and wrenches can be expressed in the space frame S or the end effector frame B. The Jacobian is a 6 by n matrix where n is the number of joints. This means that the rank of the Jacobian can be no greater than the minimum of 6 in n. We say that the Jacobian is full rank at a configuration theta if the rank is equal to the minimum of 6 in n. We say that the Jacobian is singular at a configuration theta star if the rank of the Jacobian at theta star is less than the maximum rank the Jacobian can achieve at some configuration. At a singular configuration, the robot loses the ability to move in one or more directions. We can also characterize Jacobians according to the number of joints n. If n is less than 6, the Jacobian is tall, meaning it has more rows than columns. The set of reachable configurations for the end effector is less than 6-dimensional, so we call such robots kinematically deficient. This does not mean the robot is not useful, it just means it's not capable of general motion at the end effector. An example robot is the 4-joint RRRP robot shown here, which has a 6 by 4 Jacobian. If n equals 6, the Jacobian is a 6 by 6 square matrix, as for this 6R robot. Such robots are often called general-purpose manipulators because they're capable of general 6-dimensional rigid body motions at their end effectors. If n is greater than 6, the Jacobian is fat, meaning it has more columns than rows. An example of such a robot is the 7R robot pictured here, which has a 6 by 7 Jacobian. Such robots are called redundant because they can achieve the same end effector twist with different joint velocities. This capability can be useful in a number of circumstances, allowing internal motion of the arm that is not visible in motion at the end effector. Your own arm has a redundancy like this. Keeping your hand stationary at a fixed configuration in space, you can still move your arm internally. It can be difficult to visualize 6-dimensional motion of a robot, so to illustrate the shape and rank properties of the Jacobian, we will use a simple planar example. In this example, the end effector velocity v-tip and force f-tip are 2 vectors, and Jacobian is 2 by n, where n is the number of joints. For the 3R arm shown here, the number of joints n is 3, the robot is redundant, and its 2 by 3 Jacobian matrix is full rank, meaning its rank is 2 at the configuration shown. Since Jacobian is rank 2, the robot can generate any linear velocity at its end effector, and any force applied to the end effector must be actively resisted by at least one of the joints. Using the fact that v-tip equals j theta dot, we can always calculate v-tip given the joint velocities theta dot. This figure shows the components of the endpoint velocity caused by the individual joint velocities, and we can sum them to get the end effector velocity v-tip. Since the rank of j is 2, any v-tip can be created by the joints. You can imagine asking the inverse question, given v-tip, what is theta dot? The answer to this question is not as straightforward, however, because in general, as in this case, the inverse of j does not exist, either because j is not square or because it is singular. Because this 3R robot is redundant, it turns out that for any v-tip, there is a full one-dimensional set of solutions of joint velocities that achieves v-tip. This inverse question will be addressed in more detail in Chapter 6. Moving on to forces, using the fact that tau equals j transpose times f-tip, we can always find the joint forces and torques tau that correspond to the end effector force f-tip. For the f-tip shown here, we can graphically calculate tau1, the torque about the first joint, using the relationship tau1 equals minus r1 times the magnitude of f-tip, where r1 is the vector perpendicular to f-tip from the joint to the line of force. Similarly, we can calculate the torques at joints 2 and 3. Each joint has to individually support the endpoint force f-tip. You could also imagine asking the inverse question. Given tau, what is the endpoint force f-tip? But this question is not as straightforward because the inverse of j transpose may not exist. For the 3R arm, for most random choices of joint torques, the arm will have internal motion and will not simply statically resist an externally applied force minus f-tip. Moving on, let's consider the redundant 3R arm when it is fully stretched out. The rank of the 2x3 Jacobian drops to 1, meaning the arm is at a singular configuration. Rotation at joint 1, 2, and 3 produces only vertical velocity at the end effector. No horizontal velocity can be achieved. Also, because of the singularity, a horizontal force applied at the end effector is resisted by the mechanical structure of the robot. No joint torques have to be applied. This 2R robot has a square Jacobian that has rank equal to 2 at the configuration shown. This means that any tip velocity is possible, and any force applied to the tip must be actively resisted by the joints. In this picture, the 2R robot is at a singular configuration, where only vertical velocities are possible, and horizontal forces can be passively resisted by the mechanical structure of the robot. Finally, we have a 1R robot. The Jacobian is 2x1 and is full rank, meaning the rank is equal to 1 at any configuration. This robot is kinematically deficient for the task of achieving arbitrary linear velocities at the tip, as it can only achieve linear velocities perpendicular to the link. Any horizontal force is passively resisted by the joint, while any vertical force must be actively resisted by the joint torque. In the next and final video of Chapter 5, we will characterize how close a robot is to being singular using the manipulability ellipsoid touched on in the first video of this chapter. A robot configuration is either singular or it's not. But even if a configuration is non-singular, it still may be close to being singular. The manipulability ellipsoid we saw in the first video of this chapter is one way to visualize how close a robot is to being singular. For this 2R robot, a circle of velocities in the joint space maps through the Jacobian to an ellipse of velocities at the tip of the robot, depending on the robot's configuration. As the second joint angle approaches 0, the ellipse squashes in the direction it is difficult to move and stretches in the orthogonal direction until, at the singularity, the ellipse collapses to a line segment. As we will see shortly, we can assign a measure of just how close the robot is to being singular according to how close the ellipse is to collapsing. To derive a general expression for the end effector velocity ellipsoid, let's begin by assuming the end effector's velocity is represented as the m-dimensional vector v-tip. The robot has n joints, so the Jacobian is an m by n matrix. A sphere of joint velocities, like the circle shown here, is defined by the equation theta dot transpose times theta dot equals 1. If we assume the Jacobian is invertible, which is not strictly necessary, then we can rewrite the equation as shown here. Rearranging, we get this, and rearranging once more, we get this. We summarize this equation as V tip transpose times A inverse times V tip equals 1, where A is the m by m matrix J times J transpose. The A matrix is both symmetric and positive definite, and so is its inverse. Now assume we take this same equation, but replace V tip by a generic vector x. The eigenvalues of the matrix A are called lambda 1 to lambda m, and the corresponding eigenvectors are v1 to vm. It is well known that the quadratic equation x transpose times A inverse times x equals 1 defines an ellipsoid of x values that satisfy the equation. In general, this ellipsoid is an m-1 dimensional surface in the m-dimensional space of x, but this figure shows the case where x is a 3-vector. The principal axes of the ellipsoid are aligned with the eigenvectors of A, and the half-lengths of the ellipsoid along the principal axes are the square roots of the eigenvalues. This geometric interpretation holds for any symmetric positive definite matrix A, but if we choose A equals to J times J transpose, then the x vector can be interpreted as V tip, and the ellipsoid is called the manipulability ellipsoid, resulting from the unit sphere of joint velocities. If instead we set A equal to the inverse of J times J transpose, then the x vector can be interpreted as the end-effector forces F tip, and the ellipsoid is called the force ellipsoid, resulting from a unit sphere of joint forces and torques. This figure shows the manipulability ellipsoid and the force ellipsoid for a 2R robot at a particular configuration. Since the matrix defining the manipulability ellipsoid is just the inverse of the matrix defining the force ellipsoid, the two ellipsoids have the same principal axes, and the lengths of the principal semi-axes are just the reciprocals of each other. In other words, only small forces can be applied in directions where large velocities can be attained, and only small velocities are possible in directions where large forces can be applied. Now that we can visualize the end-effector motion capabilities as a manipulability ellipsoid, we can assign a single number representing how close the robot is to being singular. These numbers are called manipulability measures. The first manipulability measure is the ratio of the longest axis to the shortest axis of the ellipsoid. This measure is lower bounded by 1, and if it is equal to 1, we say that the manipulability ellipsoid is isotropic. It is equally easy to move in any direction. On the other hand, as the robot approaches a singularity, this number grows large. The second measure is just the square of the first measure, often called the condition number of the matrix A. A final measure is the square root of the product of the eigenvalues of A, which is proportional to the volume of the manipulability ellipsoid. If the manipulability ellipsoid volume becomes large, then the force ellipsoid volume becomes small, and vice versa. Finally, consider the case that the Jacobian corresponds to the body Jacobian derived in this chapter. The 6 by n body Jacobian can be split into the 3 by n angular velocity Jacobian jb omega and the 3 by n linear velocity Jacobian jbv. The separation into linear and angular components is useful because the units of the angular velocity and linear velocity are different. Then for any configuration of the robot, jb omega can be used to create angular velocity manipulability ellipsoids and angular moment ellipsoids, and jbv can be used to create linear velocity manipulability ellipsoids and linear force ellipsoids. So this concludes Chapter 5. You should now have a solid understanding of how to derive and interpret the Jacobian, a fundamental object in robotics that is heavily used in many robot motion planners and controllers. In Chapter 6, we study another key issue in robot motion planning and control, inverse kinematics, or how to find joint positions that achieve a desired end-effector configuration. In Chapter 4, we studied the forward kinematics of open chains. Given the joint configuration theta, find the configuration of the end-effector frame B relative to the space frame S. In this chapter, we study the inverse kinematics problem. Given a desired end-effector configuration, find joint positions that achieve it. This is obviously an important problem since we have to control the end-effector's configuration for it to purposefully interact with the world. Inverse kinematics is trickier than forward kinematics. Unlike the forward kinematics, which has a unique end-effector configuration for a given set of joint values, the inverse kinematics problem may have 0, 1, or multiple solutions for the joint values theta given the desired end-effector configuration. We'll see an example of this in a moment. There are two approaches to solving the inverse kinematics problem. First, in some cases, we can find analytic closed-form solutions to the nonlinear equations. These solutions typically take advantage of geometric insight into the problem and the particular structure of the robot. For arbitrary robot kinematics, however, analytic solutions may not exist, so a second approach is to use an iterative numerical method. This approach requires an initial guess at a solution, then iteratively drives the initial guess toward a solution. Unlike analytic methods, this approach requires an initial guess and will only find one solution, not all possible solutions, but it applies to robots with arbitrary kinematics. In this video, we will analytically solve the inverse kinematics for a planar 2R robot. For this example, and indeed many of the inverse kinematics problems in robotics, it is useful to define the two-argument arctangent function. The atan2 function takes the x and y coordinates of a point in the plane and returns the angle of a vector from the origin to the point relative to the x-axis. Another useful tool is the law of cosines. If A, B, and C are the lengths of the sides of a triangle, and capital C is the interior angle opposite side C, then the length of edge C is given by c squared equals a squared plus b squared minus 2ab cosine of capital C. For a planar 2R robot, the inverse kinematics problem is to find the joint angles θ1 and θ2 such that the tip of the robot is at the point xy. The workspace of the tip of the robot is bounded by circles. The inner circle has radius L1 minus L2, and the outer circle has radius L1 plus L2. If we request a tip position xy outside the workspace, there are no inverse kinematic solutions. If we request a tip position on the boundary of the workspace, there is one solution. θ2 is pi on the inner boundary, and θ2 is 0 on the outer boundary. If we request a tip position in the interior of the workspace, then there are two solutions, as shown in the figure. For the solution shown on the right here, gamma is the angle from the x-axis to the tip, and alpha and beta are interior angles of the triangle formed by link 1, link 2, and the line from the tip to joint 1. Gamma is determined from the atan2 function, and alpha and beta are determined from the law of cosines. With these, the two solutions to the inverse kinematics for points in the interior of the workspace are shown here. The book discusses other examples of inverse kinematics, particularly for robots with 6 joints, and the atan2 function and law of cosines are useful in those examples too. In the next video, we study numerical inverse kinematics, which is useful for cases where no closed-form analytic solution exists. The forward kinematics maps the joint vector theta to the transformation matrix representing the configuration of the end effector. For simplicity, we will start instead with a coordinate-based forward kinematics, where f of theta is a minimal set of coordinates describing the end effector configuration. Then the inverse kinematics problem is to find a joint vector theta d satisfying xd minus f of theta d equals 0, where xd is the desired end effector configuration. To solve this problem, we will use the Newton-Raphson numerical root finding method. In the case that theta and f of theta are scalars, the Newton-Raphson method can be illustrated easily. Here's a plot of the desired end effector position xd minus f of theta as a function of theta. The roots of this function correspond to joint values that solve the inverse kinematics. In this example, 2 values of theta solve the inverse kinematics. Now, with the benefit of hindsight, we designate one of the solutions as theta d. We also make an initial guess at the solution, theta 0. At that guess, we can calculate the value of xd minus f of theta. Since we know the forward kinematics f of theta, we can calculate the slope of xd minus f of theta. If we extend the slope to where it crosses the theta axis, we get our new guess theta 1. The change delta theta in the guess is given by the expression in the figure. If the function xd minus f were linear, theta 1 would be an exact solution. Since it is not linear in general, theta 1 is only closer to a solution, not an exact solution. Now we can repeat the process, getting a new guess theta 2, and continue repeating until the sequence theta 0, theta 1, theta 2, etc. converges to the solution theta d. If our initial guess theta 0 had been to the left of the plateau in the function xd minus f of theta, then the iterative process may have converged to the root on the left. In general, the initial guess should be close to a solution to ensure that the process converges. If the initial guess were near the top of the plateau, the calculated slope would have been small and the next iteration would be far away, where it may be difficult to converge to a solution. To generalize the Newton-Raphson procedure to vectors of joints and endpoint coordinates, not just scalars, we can write the Taylor expansion of the function f of theta around theta d, as shown here. F of theta d is equal to f of theta I, where theta I is the current guess at the solution, plus the Jacobian of f evaluated at theta I times delta theta, plus higher order terms. If we ignore the higher order terms, this simplifies to xd minus f of theta I equals j of theta I times delta theta. We can solve for delta theta as j inverse times xd minus f of theta I. Of course, this only works if j is invertible. If j is not invertible because it is not square because the robot is at a singularity, we need a different way to calculate delta theta. Let's rewrite the equation we are trying to solve and number it 1. Instead of pre-multiplying both sides by j inverse, we could pre-multiply by the pseudo-inverse of j. The pseudo-inverse reduces to the matrix inverse in the case that j is invertible, but it can also be calculated for non-square and singular matrices. The pseudo-inverse has the following nice properties. If there exists more than one solution exactly satisfying equation 1, for instance, if a robot is redundant, then the pseudo-inverse finds a solution vector theta star that has the smallest length amongst all solutions. In other words, the change in joint values is as small as possible while still satisfying equation 1. On the other hand, if the robot is at a singularity, or if it does not have enough joints to exactly satisfy equation 1, then theta star calculated by the pseudo-inverse is one that minimizes the error in satisfying equation 1. We can now state the Newton-Raphson numerical inverse kinematics algorithm. Starting from an initial guess theta 0, we calculate the end-effector error E. If it is small enough, then theta 0 is our solution. If not, then we add pseudo-inverse of j times the error E to our guess and repeat. We can use this algorithm inside a robot controller. At every time step, an updated desired end-effector configuration xd is sent to the controller, and it calculates an appropriate joint vector using Newton-Raphson. The previous joint vector is a good initial guess to the new joint vector, since the updated xd should be close by the previous xd. In the next video, we adapt this algorithm to the case where the end-effector configuration is represented by a transformation matrix, and the Jacobian is the body Jacobian. In the previous video, we derived the Newton-Raphson numerical algorithm for inverse kinematics when the end-effector configuration is represented by a minimum set of coordinates xd. In this final video of Chapter 6, we modify the algorithm so that the desired end-effector configuration is described by the transformation matrix TSD. We also need to replace the error vector E by something else. The proper way to interpret E is as a velocity which, if the end-effector followed it for unit time, it would move from the current configuration f of theta I to the desired configuration xd. For our modified algorithm, we need to find the twist that would take the end-effector B frame to the desired frame in unit time. Let's illustrate using these three frames. The S frame is fixed in space. The D frame is the desired configuration of the end-effector, and it is represented in the S frame as TSD. The B frame is the configuration of the end-effector if the joint vector is theta I, given by the forward kinematics TSB of theta I. We can calculate the configuration of the frame D relative to the frame B as TBD equals TSB inverse times TSD. We are looking for the twist that moves the B frame to the D frame in unit time, and the matrix representation of this twist is just bracket VB equals log of TBD. If the B frame follows the body twist VB for 1 unit of time, it will end up at the desired configuration D. Thus, VB serves a similar role as the error vector E in the coordinate version of the algorithm. Now we can write the modified algorithm as shown here. We begin with an initial guess theta 0, then we calculate the matrix representation of the body twist VB that moves the B frame to the D frame. If the angular component omega B and the linear component VB of the body twist are both small, then theta 0 is a good solution to the inverse kinematics problem. Otherwise, we update our joint vector guess by adding the pseudo-inverse of the body Jacobian times the body twist VB and repeat. We apply this algorithm to the inverse kinematics of a 4-joint RRRP arm. The desired end-effector configuration is illustrated by the frame D, but our initial joint vector guess theta 0 would put the end-effector frame B at the configuration shown. Let's animate the robot to show the joint angles found at each of 4 iterations of the Newton-Raphson algorithm. This is iteration 1, then 2, then 3, and then 4. After 4 iterations, the remaining configuration error is imperceptible, and the numerical inverse kinematics algorithm has converged to a good solution. Of course, in practice, the robot would not actually move until it has calculated a solution. The animation here just visually demonstrates the iterations. Let's watch the animation one more time. We have been focusing on finding the joint positions that achieve a desired end-effector configuration, but in some cases we only need the joint velocities that achieve a desired end-effector twist. We call this the inverse velocity kinematics, where the desired twist Vd and the Jacobian J are expressed in the same frame, either the space frame S or the end-effector frame B. If the robot has more than 6 joints, the use of the pseudo-inverse ensures that the sum of the squares of the elements of theta dot is the smallest among all joint velocity vectors that achieve the desired twist. If the robot has less than 6 joints, meaning it cannot exactly achieve an arbitrary desired twist, the use of the pseudo-inverse ensures that the error of the actual twist from the desired twist minimizes the sum of squares of elements of the error. The book describes other types of inverses that yield solutions minimizing other quantities. So this concludes Chapter 6. With the forward kinematics of Chapter 4, the velocity kinematics of Chapter 5, and the inverse kinematics of Chapter 6, you are now prepared to design kinematic controllers for open-chain robots, as discussed in Chapter 11. But before we do that, in Chapter 7 we look at the forward kinematics, inverse kinematics, and velocity kinematics of closed-chain robots, which exhibit features not present in open chains. In Chapters 4, 5, and 6, we studied the forward kinematics, velocity kinematics and statics, and inverse kinematics of open-chain robots. In Chapter 7, and in this single video, I'm going to cover all of these topics for closed-chain robots without going into great detail. Kinematics and statics are generally more complicated for closed-chain robots because there's such a wide variety of design possibilities. The configuration space of closed-chain robots can be quite complex since they must satisfy a number of loop closure equations. There are classes of singularities that don't exist for open-chain robots, and the choice of which joints to actuate and which to leave passive can affect the singularities that occur. Oftentimes, the analysis of these robots is based on symmetries and insight into the specific structure of the mechanism. In this chapter, we take an example-based look at some of these issues. The study of closed-chain robots is an active research area, and this chapter just skims the surface. Let's start by looking at some examples. The first example is a 4-degree of freedom robot arm. The end effector moves in X, Y, and Z, and it rotates about a vertical axis. Although it looks similar to an open-chain robot, it is a closed chain due to the parallelogram type linkage. The next example is a 4-degree of freedom delta robot. The end effector moves in X, Y, and Z, and it rotates about a vertical axis. There are also 3-degree of freedom delta robots that eliminate the rotational motion. The final example is the Stewart platform, which moves with the full 6 degrees of freedom of a rigid body. Each of the 6 legs is actuated by a prismatic joint. At one end of each leg is a spherical joint, while the other end has a spherical or universal joint. The Stewart platform is popular for applications like aircraft simulators, since it can move the virtual cockpit with all 6 degrees of freedom. The Delta robot and the Stewart platform are examples of parallel robots. A parallel robot is a specific type of closed chain which consists of a moving platform attached to a base through a set of actuated legs. For the rest of this video, I'll focus on parallel robots. Let's summarize some typical characteristics of open chain and parallel robots. For an open chain robot, typically each joint has a motor driving it. For parallel robots, many of the joints are unactuated. Open chain robots tend to have a large workspace since each extra joint adds to the possible motion of the end effector. Parallel robots tend to have a small workspace since each leg in parallel places constraints on the motion of the platform. Each joint of an open chain robot has to support all of the end effector force, so open chain robots tend to be relatively weak. Also, flexibility at the joints and links tend to add. Parallel robots, on the other hand, tend to be stiff and strong since the end effector force is distributed among the legs. As we saw in Chapter 4, the forward kinematics mapping joint values to end effector configurations is relatively easy to evaluate for open chain robots using the product of exponentials. On the other hand, there may be multiple solutions to the forward kinematics for parallel robots, and finding them can be challenging. Finally, as we saw in Chapter 6, solving the inverse kinematics for an open chain robot can be tricky. There may be multiple solutions, and numerical methods may be required to find them. The inverse kinematics of a parallel robot is sometimes straightforward, as we will see. To solidify our understanding of these characteristics, let's use the Stewart platform as an example. The fixed frame is S, and the end effector frame is B. The configuration of the B frame relative to the S frame is TSB of theta, where theta is the vector of joint variables representing the leg lengths. For the ith leg, theta I is the length of the leg. AIS is the vector from the S frame to leg I's joint at the base, measured in the S frame, and BIB is the vector from the B frame to the top joint of leg I, measured in the B frame. We can transform BIB to the S frame by pre-multiplying by the desired end effector configuration, TSB, provided we represent the vectors in homogeneous coordinates. Now we can calculate the prismatic joint value theta I as the distance between BIS and AIS. Inverse kinematics is easy for the Stewart platform. If the legs of the parallel robot are more general open chains, then we have to solve an inverse kinematics problem for each leg. Next, let's address the inverse velocity kinematics mapping the end effector twist to the joint velocities. Let v hat I be the unit 3 vector aligned with the direction of positive motion of the ith axis. Skipping the straightforward derivation, we can define a screw axis vi expressed in the S frame with the linear component v hat I and the angular component AIS cross v hat I. Then the joint velocity theta dot I is equal to the screw axis vi dotted with the spatial twist vs. This calculates the component of vs along the joint axis. Repeating this analysis for all the legs, we can write the ith row of the inverse of the space Jacobian, or JS inverse, as the screw axis VI transpose. Now, if the Jacobian inverse is invertible, we have the velocity kinematics and statics in the S frame. The spatial twist Vs equals Js times theta dot, and the joint forces tau equals Js transpose times Fs, the wrench applied by the end effector. One of the difficulties of analyzing closed chain robots, however, is understanding all the possible singularities where the Jacobian is not invertible. Let's consider a simpler robot, the 3x-RPR parallel mechanism, which is the planar analog of the Stewart platform. The platform moves in all 3 planar degrees of freedom and is driven by 3 legs. Each leg has 2 unactuated revolute joints and 1 actuated prismatic joint. If we put the robot at this configuration, it is at a singularity. From this configuration, if we extend the legs at an equal rate, the platform could either rotate counterclockwise or clockwise, and we can't predict which. Closed chains can be subject to several types of singularities described in detail in the book, some of which have no analogs in open chain robots. Examples include configuration space singularities, actuator singularities, and end-effector singularities. Some of these singularities occur at configurations where the constraint Jacobian, which is the matrix of derivatives of the loop closure equations with respect to the passive and actuated joint variables, loses rank. Lastly, we addressed the forward kinematics problem for closed chains, which was the first problem we addressed for open chains. The forward kinematics problem often involves solving one or more complex nonlinear equations, and in general, the forward kinematics has multiple possible solutions. The 3x-RPR robot can have up to 6 possible end-effector configurations given a set of prismatic joint extensions. This figure shows 2 possible solutions when all joint extensions are equal. The 6-Doff-Stewart platform can have up to 40 solutions for a given set of leg extensions. For a given set of leg extensions, usually there are far fewer real solutions. In practice, it is common to use iterative numerical methods with a nearby solution as an initial guess, similar to the Newton-Raphson method we developed for the inverse kinematics of open chains. In this video, I have given you a quick summary of the topics of Chapter 7, which itself is a quick summary of the kinematic analysis of closed-chain robots. The design and analysis of closed-chain robots is an active research field, but Chapter 7 should give you a good idea of some of the key issues. So as Chapter 7 concludes, so does our kinematic and static analysis of robots. In Chapter 8, we will begin our study of robot dynamics, which governs how a robot moves when forces and torques are applied at joints. This will be our springboard to advanced topics, like the design of time-optimal trajectories and controllers for robots.